Hello grade 10s, welcome back to another video with me, Miss Martins. In today's video, we're going to be looking at past paper practice for waves, electrostatics and electric circuits or electricity. This is technically a term 1 past paper revision video. However, you can use this if you're writing in June, November, whatever time of the year, because as long as it's on those sections, you can use this video as practice to help you with those sections. Please don't forget to subscribe for more maths, more physics, more chemistry. As a teacher, I'm here to help you level up your marks, so you don't want to miss the video. I give teacher tips all throughout the video. So let's jump right in. Let's start off with some multiple choice questions. Now, multiple choice in physics and chemistry, as you may or may not know, requires you just to write the letter of the question. So, for example, in this case, on your question paper, on your answer sheet, you'll write 1.1, and then you'll choose the correct answer. So you'll just write the letter of your choice next to 1.1. That's it. You don't need to write out the word. So they say there's only one correct answer. Write down the letter next to the question number. So the maximum displacement of a particle from its rest position is known as its, and the answer for this question is amplitude. So you will write 1.1 B, and you'll get 2 marks for that because that's the correct answer. Now, this is obviously a waves question, and this is a definition question. So the maximum displacement of a particle from its rest position, that is the definition for amplitude of a wave. So if you learn your definitions, you'll be fine with that question. But just as a means of recapping, this is the rest position, okay, this equilibrium position or the rest position, and the maximum displacement of a particle from its rest position, so basically the maximum amount that, or the maximum distance that it moves from its rest position, that's there to there, that is known as the amplitude, or from here to here. That is the amplitude of a wave. 1.2 says, which one of the following statements is true? Sound waves can travel in a vacuum. Sound waves are electromagnetic waves. The speed of waves, the speed of sound waves, is always constant, and the pitch of a sound wave is dependent on its frequency. So they want to know which one of these is true. Now, first of all, A is not true. It's not sound waves that travel in a vacuum. It's electromagnetic waves that travel in a vacuum. Sound waves need a medium to travel through, like air or water, so that's not true. Sound waves are electromagnetic waves. That's not true. Sound waves are longitudinal waves. The speed of sound waves is always constant. That's not true. It depends. It depends on a lot of things. The speed of light is what is constant. Remember, the speed of light is c, and it's 3 times 10 to the 8 meters per second. But the speed of sound is not always constant. It can vary. So D is correct. The pitch of a sound wave is dependent on its frequency. High frequency, high pitch. Low frequency, low pitch. So your answer for 1.2 is D. 1.3, the diagram below represents 2 sound waves, A and B. Just be careful because the first one is B, the second one is A. And they say which of the following combinations that compares the frequency and loudness of A and B is correct. Now, before I even look at the options, I just want to remind you of 2 things. Loudness, okay, because they want us to compare frequency and loudness. Loudness is related to amplitude of the wave. So the bigger the amplitude, the louder the wave. So let's just look at loudness purely first. B has a much smaller amplitude than A. If you look at how high B is, so remember amplitude is the maximum displacement of a particle from its rest position. So starting at the equilibrium line to the crest of the wave. Starting at the equilibrium line to the crest of the wave. A has a bigger amplitude, so it's a bigger loudness. So when we choose or when we select our correct answer here, the loudness of A must be greater than the loudness of B. So it's either going to be this option or this option. These options are immediately out of the running because we know the loudness of A must be greater than the loudness of B. The amplitude is bigger. Then, frequency. So frequency, you need to learn that frequency is the number of waves that pass in a second, or the number of waves or wavelengths that pass a given point in a second. So if we pretend that this represents 1 second, okay, 1 second of B, and let's pretend that this represents 1 second of A. How many waves passed for 1 second of B? That's 1 wave. That's 2 waves. So 2 waves in 1 second for B. What about for A? That's 1 wave. That's 2 waves. So 2 waves for A. So if 2 waves pass in 1 second for B and 2 waves pass in 1 second for A, it means that they have the same number of waves that pass in 1 second, which means that the frequency is the same. So immediately that eliminates this option, and our answer is D. Frequency is the same as B, but the loudness is greater than. So a big tip that I can give for multiple choice questions is often to use process of elimination. So you see how I eliminated A, B, and C, so therefore I knew D was the answer. 1.5. Which one of the following statements best describe the behavior of an electromagnetic wave? Now, this is something that you need to study. Okay, again, by process of elimination, we'll be able to eliminate the ones that are obviously not true. And the ones that should be obviously not true is anything that has to do with stationary. So you should know that an electromagnetic wave consists of varying electric and magnetic fields. Okay, they move in relation to one another, but neither of them is stationary. So we can already eliminate option C and option D because they speak about one of them being stationary, and yeah, they're both stationary. That's not true. You need to know, according to the definition, it's all about electric and magnetic fields vibrating perpendicularly to one another. So if you go to my video on electromagnetic waves, electromagnetic radiation, I explain exactly what this looks like. So your answer is A. 1.5. This one is quite challenging. So it says a learner has determined the charges on various objects. Which value has been incorrectly calculated? Now, if you don't know your work and if you don't understand the formulas and the principles, this question is going to seem very random. Like, how are we supposed to know which one is incorrectly calculated? But this is based on the principle of charge quantization, which is one of the principles that you need to know in electrostatics. I do have videos on that. I'll link it below. But basically what it says is that all charges, so all the charges on all the objects, are integer multiples of the charge of an electron. Okay? These are the formulas related to that. This formula is the same as this formula, it's just rearranged. So this is the formula they give you on the formula sheet. If I want to isolate Q as my variable, I take QE over and it becomes N times QE. Now, if you haven't seen my video on that or you don't know about it, QE is the charge of an electron. Okay, charge of an electron. And that is a set value, it's a constant. It's negative 1.6 times 10 to the negative 19. N is what we call number of electrons. Number of electrons. And that can only be an integer. So it's that is basically what the charge of quantization says. It says the charge of all objects in the universe consists of an integer multiple of the charge of an electron, which means that an object can have a charge of 1 times 1.6 times 10 to the negative 19, or 2 times 1.6 times 10 to the negative 19, or 3 times 1.6 times 10 to the negative 19, but not 1.5 times 1.6 times 10 to the negative 19. So it has to be an integer. So how we would figure out which of these is incorrect is we would take each of them and divide each of them by the charge of an electron. And I'm just going to use the positive, the absolute value. It doesn't have to be negative. I divide each of them by 1.6 times 10 to the negative 19, and I look for which one of them give me integer values for n. So 1, 2, 3, 4, 5. If it does not give me an integer value of n, then that charge is not possible. So I divide each of them by 1.6 times 10 to the negative 19. So basically this is Q, and I'm dividing it by QE. And remember, Q divided by QE gives me N, and we're basically looking to see integer values of N, not decimal values of N. So if I take each of those, A, B, C, D, divided by 1.6 times 10 to the negative 19, this is what I get. So all of these options, A, B, C, they all give me an integer for N. So N is 6 electrons. N is 4, N is 3. This one is, N is 2.5. So that cannot be the correct charge. So D is our answer over here. Right, moving on to 1.6, our last multiple choice question. The voltmeter below reads 8 volts. Okay, so we've got this voltmeter reading 8 volts. They want to know the EMF of the battery. Now, remember, EMF in grade 10, we don't care about internal resistance of the battery. So the EMF is basically the reading of the voltmeter across the battery. So they want to know, if this is 8 volts, what's this reading? Now, because I have another resistor connected here in series, what you should know about electric circuits, electricity, is that resistors in series, so these are resistors in series. Resistors in series are voltage dividers, or resistors in series split or divide the voltage. So what that means is that the voltage across the 10 ohm resistor, which is 8 volts, and the voltage across the 5 ohm resistor, which I don't know, if I add those two together, it'll give me the voltage across the battery or the EMF of the battery. So this option is immediately not correct, because 8 plus something must give me the voltage across the battery. So this option can only be correct if this is 0 volts. And that can't be. It can't be 0 volts, because as soon as this voltmeter is connected across something that has a resistance, this can't be 0 volts. It has to have voltage. It also can't be 6 volts. It also can't be 4 volts, because how can it be less than the voltage on this resistor? The only option here is 12 volts, but I want to show you how you would work that out even if they didn't tell you it was 12. So how you would work it out is as follows. We know the voltage across the 10 ohm resistor is 8 volts. Then they give us a 5 ohm resistor. What is the relationship between the 10 ohm and the 5 ohm? Well, the 5 ohm resistor is half the size of the 10 ohm resistor. So you basically divide the resistance by 2. So 10 divided by 2, you get 5 ohms. Now, if I divide the resistance by 2, it means it has a smaller resistance, which means it'll have a smaller voltage. So that means to get this voltage over here, I would have to divide this by 2, and this voltmeter would read 4 volts. And then you simply say, well, I'm looking for the voltmeter reading across the battery, which means I must take this voltmeter reading 8 volts and this voltmeter reading 4 volts, and that's where the 12 volt answer comes from for the reading across the battery or the EMF of the battery. Now, you could be thinking, ma'am, how did you know that if you divide this by 2, you must also divide this by 2? The reason I knew that is because of the way that the variables are related to each other in this formula. So you need to be familiar with this formula, and I need this to make sense. I need you to understand this. Because the 10 ohm resistor and the 5 ohm resistor are in series, so they're connected in series, the current that flows through them will be the same. That's why I said, yeah, the current is the same. What that means is bigger resistance, bigger voltage. Think about it. If I have to keep current the same, if I make R bigger, this number over here is going to get bigger. And that means that voltage is directly proportional to resistance. If resistance gets bigger, voltage gets bigger. And in the same way, if resistance is smaller, voltage is going to be smaller. So if resistance is halved, voltage must be halved. I hope that makes sense. In this case, it was quite easy to find the answer anyway by process of elimination. Right. Those are the multiple choice questions. As I've mentioned, they can be quite tricky, but let's move on to question 2 in the paper, which has to do with waves. And this has to do with transverse waves, and in particular, transverse pulses. So it says the diagram below shows 2 pulses P and Q traveling in opposite directions. P is traveling to the right. Q, they show with an arrow, is traveling to the left. They're in the same medium, so it could be water, it could be air, doesn't matter. The amplitude of pulse P is 3 centimeters, so they give me that amplitude. And that of pulse Q is unknown. I don't know what this is, okay? Unknown. So I'm going to call it, you can call it X or you can call it whatever. I'm just going to call it Q. It's an unknown amplitude. Remember, they are heading towards each other, these pulses. So at some point, they're going to occupy the same space at the same time. And it's going to be the principle of superposition when two pulses occupy the same space at the same time, and we need to determine what that resultant pulse is by using the sum of the pulses. The two pulses meet at point X. The resulting amplitude is shown below. So 5 centimeters, but going downwards. Right, let's see what questions they have for us. These are the questions that we're going to be looking at. The first one is a definition. Define the term pulse for 2 marks. This is a study definition. You just study it and you regurgitate the answer. And a pulse is a single disturbance in a medium. 2 marks for that definition. Easy. And next question. What type of interference takes place at X? Now you need to know that there's 2 different types of interference. There's constructive interference and destructive interference. I do have a video on this. I'll link it in the description box below. But we can see that P had an amplitude of 3 going upwards. Q had quite a big amplitude of unknown value going downwards. But ultimately, the amplitude was going downwards, but less of. I don't know if you can tell, but this had a little crest. This had quite a big trough. And this has like an intermediate sized trough. What type of interference is that? It's destructive interference. Constructive interference is, for example, if I had a crest like that and I had a bigger crest like that and they're heading towards each other and then they combine to make a big crest. That would be constructive interference. This is clear destructive interference. Okay. Right. 2.3. Determine the amplitude of Q. I know if you look at that, you can probably figure it out. If this is 3 going up, and then some unknown value going down, and afterwards the resultant is still 5 going down, I hope it makes sense to you that this must be 8 centimeters. Now, if that doesn't make sense to you, how can you figure that out otherwise? Well, we've got P plus Q, and that gives me position X. Now, because P is going up and Q is going down, I need to choose one of my directions as a positive direction. I'm going to choose up as a positive direction. I'll show you what I mean by this now. So because P is going up, it's going to be a positive. Q, I'm not sure what it is, so I'm going to leave it as plus Q. And X, when they meet, okay, it's the algebraic sum. So P plus Q, adding those two together, it gives me situation X. That's why I'm adding them. It's the algebraic sum of the 2 pulses. X is 5, but it's going down. So remember, I said up is a positive, so that's why it's a positive 3. X is going down, so it's a negative 5. If I take 3 to the other side, it's going to be negative 5 minus 3. What does that get me? It gets me negative 8. And remember, what the negative means is it just means 8 centimeters going downwards. So basically, it's a little trough that looks like that. And that is exactly what we said Q was, 8 centimeters. Okay, let me just show you, because I know that this can be quite confusing. If these pulses were heading towards each other, you see 1 centimeter is going up and 3 centimeters is going up. So let's call this one Q and let's call this one P. And when they meet, that's point X. So we'll say Q plus P equals X. Because they're both going up, I'm going to say up is positive. It'll be a positive 1 and a positive 3. And X will be positive 4. And that makes sense because it'll create a bigger crest with the amplitude of 4 centimeters. I hope that makes sense. But as soon as one of them is going downwards, then one of the directions has to be positive, the other has to be negative. So P plus Q, together it must give me X. Okay, it's just an algebraic sum. It's in the definition. So 3 is positive because it's going up. Q, I do not know. Don't make it a negative. We don't know what it is. So leave it as plus Q.
And 5, because it's going down, is a negative, and then you solve for Q. 2.4 says a learner states that immediately after pulses P and Q meet at point X, pulse P will move to the left. Is the learner's observation correct? Answer yes or no. So let's just think about this. P was initially going to the right. Q was going to the left. They meet at point X, which is over here. And that's what happens when they meet. When they're done meeting, P was initially going to the right. P will continue moving to the right. Q was initially going left. It will continue going to the left. So the learner saying that P will move to the left is wrong. The observation is not correct. P will continue moving to the right. Use a physics principle to explain the answer. So the physics principle that we use is the principle of superposition. Again, you need to study this. I have videos on this linked down below. But basically, the principle of superposition says that the pulses continue to move in their original direction. So because P was initially going to the right, it will continue moving to the right. Okay, question 3 is a transverse wave question. So we had a transverse pulses question. Now we're on a transverse waves question. And I know that learners struggle with this one, so I hope you pay attention to this one. We've got the wave pattern is produced by a wave that takes 2.5 seconds to complete one wave cycle. A particle at point B, there's B, vibrates at 90 degrees to the direction in which the waves are moving. Now, a few things that we can see from here immediately before we even look at the questions. These are the questions, by the way. But before we even get into them, I want us to notice one thing. The particle at B vibrates at 90 degrees to the direction in which the wave is moving. That means that B will go up or down. The wave, look here, wave direction is going to the right. So the wave is going to the right. Particle is moving up or down. That's at 90 degrees. And the definition of that type of wave is a transverse wave. The particles of the medium vibrate perpendicularly or vibrate at 90 degrees or at right angles to the direction of motion of the wave. Another piece of information that we can get from reading carefully is that it takes 2.5 seconds to complete one wave cycle. They could say to complete one wave. They could say to complete one wavelength. They could say for one crest to pass. But all of this is telling me the same information. And that is the period of the wave. Period is represented by the symbol T. You need to study your theory. And the theory says that period, the definition of period, is the time taken for one complete wave cycle or for one complete wave pulse to pass a given point. So this 2.5 seconds is period, and that makes sense because period is measured in seconds. So we know period. Right. What type of wave is indicated in the diagram above? You're going to say a transverse wave, and we discussed why it's a transverse wave. We discussed that they basically give the definition for the transverse wave. Give one reason why a particle at B is out of phase with a particle at C. Now, one of the reasons is because in phase and out of phase has to do with the number of complete wavelengths that separate points. So, for example, this point of the wave over here and this point of the wave over here will be in phase because they're separated by one wavelength. This point over here and this point over here will be in phase because they're separated by two complete wavelengths. So it's whole numbers of wavelengths. But this particle over here and this particle over here won't be in phase because they're separated basically by half a wavelength, not a whole number of wavelengths. So that's one of the reasons why B and C are out of phase. They are separated by half a wavelength or not a whole number of wavelengths. The other reason is because of the directions that they will be moving in. So to figure out the direction that B and C will be moving in is imagine redrawing this wave kind of like 1 second later. Now, what I'm drawing here is a bit confusing, but imagine the original wave, okay, that the computer drew in, shifted to the right slightly. Okay, so just imagine that. The original wave, so here, that's the original, now shifted to the right very, very slightly, which I did over here. You can kind of see that the yellow one I've shifted slightly to the right. compared to the green one. So instead of B being over here, it's over there, and instead of C being over there, it's over there. Or instead of the trough being over there, it's there, and instead of the crest being over there, it's there. If I want to figure out which way B would move next, we take B, where B is, and you draw a dotted line like that. You take where C is, and you draw a dotted line like that. Where's B? On the green wave, it's over there. On the yellow wave, it would be over here on the same dotted line. So B would be moving upwards. So B would move up. C is over here on the green wave. On the same dotted line, follow it down. That's where C would be on the yellow wave. So C is moving down. So because they're moving in opposite directions, that's also another indication that they are out of phase. So there's 2 reasons. You need to choose one of the 2 reasons. 3.3 says determine the frequency of this wave. Now remember, we already discussed that 2.5 seconds is the period. Period is 2.5 seconds. You need to know that in order to go from period to frequency, we simply use the following formula. Frequency is equal to 1 over period. They are reciprocals of one another. And I just want you to remember, grade 10s, that you will always be able to refer to your formula sheets in your exam. So the formula that they give you, generally they give both. Period is 1 over frequency, and frequency is 1 over period. So we can refer to the formula sheet to give me my formulas, and that will be the formula that I use. Now take note that frequency also appears in this formula. However, I will show you why that's not necessarily the right formula or a helpful formula to use. So the other formula that frequency appears in is this formula. But I don't know the wave speed and I don't know the wavelength. So this formula doesn't make sense. I'm going to use this formula. Period is 2.5. So you type that in onto your calculator. It is 1 divided by 2.5. It's the reciprocal of my period. And that is 0.4 hertz. You get a mark for your blank formula, you get a mark for substitution, and you get a mark for answer with a unit. If you leave out your unit, you lose your answer mark. They say if the speed of the wave is 0.08 meters per second, calculate the value of x in meters. Now this is 4 marks. And seeing that this is 4 marks should tell you that there's quite a little bit of working out that we need to do over here. So before we get into the question, I want us to write down what we already know. We know the period is 2.5 seconds. We know the frequency is 0.4 hertz. That's all we know so far. Do we know anything else? No, we don't know anything else. They also tell me in the question the speed of the wave. So speed of the wave, you should know if you studied and if you watch my other videos, speed of wave is v 0.08 meters per second. Now they want me to calculate the value of x in meters. First things first, what can I get from this information that is measured in meters? I just showed you a formula that looked like this. Which of these 3 variables is measured in meters? Well, that is speed. That's measured in meters per second that I gave you. This is frequency. It's measured in hertz that I gave you. This over here, remember, is wavelength. And wavelength is measured in meters. So you're thinking to yourself, okay, cool. I'm going to apply this formula, which is the correct thing to do. You write your formula first. You substitute your values in. V is the speed of the wave. They gave it to me in the question, 0.08. Frequency, I worked out in the previous question, 0.4. And I'm going to work out wavelength. How do you get wavelength by itself? This is times 0.4. So you must say 0.08 divided by 0.4. Because divide is the opposite of times. And these are being times. So the wavelength is 0.2 meters. Now you might think, cool, I'm done with the question. I worked out the meters thing. They said they wanted me to calculate the value of x in meters. But this question is not done. You need to think about what this means. What does this thing mean that you just calculated? Wavelength. Wavelength is the distance for one wave. It is the distance between 2 consecutive points in phase. That's what wavelength is. That's the definition. It's for one wave. They want the distance for distance x. And what's important for you to note is that distance x is not for one wave. Look at what distance x includes. Distance x starts here and it ends here. Let's join those dots. So it starts there, it goes there, and it ends there. That yellow highlighted piece is not one wave. How many waves are in this yellow highlighted piece? Well, if we start at A over here, that is one wave. Okay, so that's one wave. That would be a half a wave. And that would be a quarter of a wave. Let's use a different color. It's very difficult to see that. Let's try orange. Okay, so how did I know that? One wave is the distance between two consecutive points in phase. So that point, my diagram is way too colorful right now. That point and that point are consecutive points in phase. And if you can't see it, think of it like this. This point is on the equilibrium line and it's just before we get to a crest. This point is also on the equilibrium line and it's just before we get to a crest. Take note that this point is not in phase with this point. I know they're both on the equilibrium line, but this one is just before a crest and this one's just after a crest. So the two red dots are points in phase. And if I join up those 2 points in phase, I get one wave. So that's one wave. Remember, that purple is one wave. So the distance between there and there, that is 0.2 meters. But that's not what the question asked for. It didn't ask for the distance between the two red dots. It asked for this distance x. And all you basically need to do, as I've mentioned already, is count the number of waves that fit in distance x. So one more time, that's one wave. Maybe it helps if you see it like this. That would be two waves, but distance x ends over here. It doesn't include that little bit, and that little bit is a quarter of a wave. So basically distance x is one wave, one full wave, the yellow wave, and 3/4 of a wave, that orange piece, or 1.75 waves. So how we get our final answer is you take the number of waves in distance x, 1.75, and we times it by the wavelength of one wave, 0.2 meters, which we just calculated over there. That comes from there. And you work that out on your calculator. So 0.2 times 1.75, and I get 0.35 meters. And you get your marks for formula, substitution, then for getting this answer, the wavelength correct, and then for your final answer, 4 marks. 3.5 is also a tricky question. They say, how long in seconds does it take for a particle to move from A to D? Now, they say in seconds. What we know so far with regards to seconds is the period. The period is 2.5 seconds. And remember what I told you about the definition of period? Period is the time that it takes for one wave to complete itself. Okay, so it takes 2.5 seconds to go for one wave. They want to know how long does it take to go from A to D. So basically what you need to do is you need to calculate or count how many waves are there from A to D. So if one wave takes 2.5 seconds, two waves would take 5 seconds because 2.5 times 2. 3 waves would take 2.5 times 3, and so on. I don't know how many waves there are. I don't know if there's 1 wave, 2 waves, 3 waves, 4 waves, 5 waves, but we can count it. So from A to D, how many waves are there? That's 1 wave. That's 2 waves. That's 3 waves. And I hope you can see that that last little bit is not a full wave. That is half a wave. So we've got 1 full wave, 2 full waves, 3 full waves, and then instead of a peak and a trough like that, we've just got a little peak. So it's 3.5 waves. So basically from A to D, there are 3.5 waves. So you take the time that it takes for 1 wave, which is 2.5 seconds. That's for 1 wave. And we times it by 3.5 because there's 3.5 waves. And what we get is our answer, which is 8.75 seconds. And I just looked at the memo of this paper. What they do is they actually just give you 2 marks for the answer, but some papers might give you 1 mark for the working out and 1 mark for the answer. So rather just show your working out and your answer. Now, just a teacher tip, please. When we mark exams and all the way up to matric, we only give you S as an acceptable unit or seconds as an acceptable unit, not sec. Please don't answer with that as a unit. We will mark you wrong. Question 4 is all about sound waves or longitudinal waves. They say a wave source on a ship sends out sound waves. So as soon as you see sound waves, you know you're dealing with longitudinal waves. They're also mechanical waves, just like transverse waves. Okay, the frequency is 25 kilohertz. So frequency 25 kilohertz. What you do need to know is that 1 kilohertz is equal to 1,000 hertz. Okay, cool. So they send the frequency out to the bottom of the sea. A receiver attached to the ship detects these waves a short while later. The speed of sound in water is 1,500 meters per second. That is V. The speed of sound. Speed is V. Now, the first question says, what is an echo? And we know that an echo is happening here because we have a ship. The ship is on the water. So here's the water. It's sending out a signal to the bottom of the sea. And then they say the receiver attached to the bottom of the ship is detecting the waves a short while later. So why would it be detecting the waves? The wave obviously hit the bottom of the ocean floor and was reflected back upwards. There was an echo. So it's kind of like if you stand on the edge of a cliff and you shout, hello, and then the sound comes back to you and it says, hello, that's an echo. So an echo is a reflection of a sound wave. That's what an echo is. That's 4.1's answer. 4.2 says calculate the wavelength of these waves. Now, once again, we're able to visit our formula sheet. And if you visit your formula sheet, we know we want wavelength. The formula that makes sense to be used in this context is, once again, this formula. I'm going to write it a bit bigger for you, and I'll explain why that is the formula that makes sense to be used. Because we want wavelength. Wavelength is represented by that symbol. The formula says that. We want wavelength. That's by unknown. We know the frequency and we know the speed of sound. Speed of sound, the speed of the waves, is 1,500 meters per second. Frequency, we have to convert to hertz. So the frequency is 25 kilohertz. If we convert that to hertz, remember, we must times by 1,000, because 1 kilohertz is 1,000 hertz. So we times it by 1,000. So our frequency is 25,000 hertz. So 25,000, and then we're looking for wavelength. So to get wavelength alone, this is times 25,000. So we have to divide by 25,000. So it's 1,500 divided by 25,000. And our answer for wavelength is 0,06, and our unit is meters. So 3 marks, and our 3 marks are for our formula, our blank formula with nothing in it, substitution, which is when we put our values in, and answer with units. Wavelength is measured in meters. Can these sound waves be heard by the human ear? Give a reason, and this is study work, but no, they cannot be heard by the human ear because it's above the detectable range that humans can hear. It's actually ultrasound. If it's above a certain frequency, and I do include this in my video, so linked in the description box below, but then it's called ultrasound. So the answer is no. The frequency is beyond the range of that for humans. 4.4. So calculate the depth of the water beneath the ship if the waves are detected by the receiver 10 seconds after being emitted. So remember, we have ship, this is a little ship over there, on the water. It sends out a sound wave, it hits the bottom of the ocean floor, and it returns back to the ship where a receiver picks up the wave again. So there's an echo. It takes time to travel down. It takes the same amount of time to travel back up. It's detected 10 seconds after being emitted. So the whole process takes 10 seconds, which means it takes 5 seconds to go down and another 5 seconds to go up. 5 plus 5 is 10. Half the time to go down, half the time to go up. And they want to know, how deep is this water? So they're looking for the distance from here to here. Now, grade 10s, I hope it makes sense that if we're looking for the depth, we're not looking for the total distance traveled by the wave. So we're not looking for how far was it to go down and then back up again. That would be the total distance traveled by the wave. We're not looking for the total distance traveled by the wave. We're looking for the depth of the water, which means we won't use the total time traveled by the wave. We'll use half of the time because it took 5 seconds to go for the entire depth. It took 5 seconds to go from the ship to the bottom of the ocean floor. And that is the distance that I'm looking for. So the time that it takes to go from the ship to the bottom of the ocean floor, so remember I'm looking for that depth, is 5 seconds. So we'll use the time that it takes. We're looking for that depth. We're basically looking for distance or displacement. This is the symbol for distance or displacement, which will give me the depth. If I know how far this distance is, I know how deep this ship is, or how deep this water is. So that's what I'm looking for. I'm looking for depth. I know the speed. The speed of sound is 1,500 meters per second. I also know other things now. I know my wavelength is 0.06 meters. I also know my frequency is 25,000 hertz. But if you get a question like this, we don't care about frequency. We don't care about wavelength. All I need to do is a speed, distance, time calculation. And I hope you remember from grade 9 and maybe even from other sections in grade 10 physics that we've got distance, speed, and time. Now, instead of distance, I'm using this symbol. It's called delta x, which is distance or displacement. Instead of speed, S, I'm using V. And time, I'm using delta t. You may have seen this before, but basically what this is telling me is that speed is equal to distance over time. That is something that you should be familiar with from grade 9. And that is actually the version that the memo uses. But speed, remember, is speed of sound. Distance, I'm just calling it delta x, and time. It means the same thing. You don't have to write it like that. You can write it like this. Speed is distance over time. And if you want to use that triangle once more, which you should have been taught in grade 9 maths, it's dsT. Speed is equal to distance divided by time. Now, I'm looking for the distance. The time that it takes to go from the ship to the bottom of the ocean floor, that time is 5 seconds. Remember, 10 seconds is going to the floor and back. I don't care about going back. I just want to know how long does it take to go from the ship to the floor because I want to work out that depth. So it's 5. And the speed is the speed of sound, 1,500. So distance is 1,500. And you multiply that by 5. And we get 7,500 meters. So where you get your marks is for that, you get a substitution mark there, there, and there. Now, if you decided to use the 10 seconds instead, you could have. So if you wanted to use the full 10 seconds, that's fine. That would then be 15,000. That would be 15,000 meters. That's a distance. But just remember, that would be the distance from the ship to the ocean floor and back. So then your final step would be taking that distance and dividing it by 2, which would get you 7,500 meters anyways. So you have two options. You either do it like this, and then you have to divide it by 2, or you do it like this, where you just use half of the time. Our next question is still dealing with waves. We're dealing with electromagnetic waves or the electromagnetic spectrum. These are the questions coming up. So my first question is briefly, what is meant by the dual nature of electromagnetic radiation? And I do cover this in my electromagnetic radiation introduction video, also linked in the description box below. But dual nature just means that electromagnetic radiation acts as a wave and as a particle. Dual means two, double nature basically. Right, my next question says name the type of electromagnetic radiation that is used to sterilize medical equipment. And that answer is ultraviolet waves. Now, again, these are things that you have to study. I do go over this in the video that I just mentioned. and which one has the longest wavelength. So the one that has the longest wavelength has the lowest frequency and also the lowest energy. So how I remember it is it's kind of like the safest of the electromagnetic radiations is the longest wavelength, has the lowest frequency, lowest energy. So long wavelength, so in other words, wavelength is very big, means that frequency is very small, so energy is very small, so it's not very harmful. And that corresponds to radio waves. Radio waves, they transmitted over massive distances, which is why the wavelength is so long. It's huge wavelengths like this. Think about it, it has to travel over long distances, and it makes sense because it's used in communication and cell phones and TVs. So that's also how I remember it. The other way I remember it is the other end of the spectrum is gamma rays, and gamma rays are super dangerous. They have a high energy, which means they have a high frequency, which means they have a small wavelength. Okay, opposite ends of the spectrum. State one danger of ultraviolet light. Again, this is study work, but ultraviolet light, UV radiation, comes from the sun and it can cause skin cancer. That is one of the major concerns about UV radiation, and it's why you must always wear your sunblock. Now, 5.4 is our calculation question in this section of the paper, and it's worth 5 marks, which means we're going to be doing quite a lot of calculating. They say a photon, remember a photon is a packet or a pocket of energy found in light. So a photon of electromagnetic waves has a wavelength of 700 nm. Now, first of all, wavelength is this, wavelength. And they say 700 nm. Nm is nanometers. Now, I go over the conversions in my video about electromagnetic radiation, but to convert from nanometers to meters, we need to times by 10 to the power of -9. There are other conversions as well, like micrometers to meters. That's times 10 to the -6. Millimeters to meters is times 10 to the -3. And then we got picometers to meters is times 10 to the -12. You need to learn these off by heart. So nano and 9. That's how I remember it. In nano 9. So we need to convert that to meters. Always must be in meters. So it's 700 times 10 to the -9 meters. And what they want is energy associated with this photon. So let's look at our formula sheet. We have wavelength. We want energy. This isn't actually too much work if you know your formulas and you use the correct one. What we have to use is actually a combination of this formula and this formula. Now, on this particular formula sheet for this particular exam, they didn't give the formula that combines these two, but I do go over this in my video, and some formula sheets do give the combined version, and it looks like this. And like I said, this formula, all it is it's this one and this one combined, and some formula sheets give it to you. Now, what I want you to notice is E is energy. That is wavelength. H is a constant, which means it'll always be a certain value. C is a constant, which means it'll always be a certain value. And those are given on your formula sheet over here. So here's H. It'll always be that. Here's H. Here's C. It will always be that. So this question is actually not very difficult. All they want us to do is to basically use that combined formula. E equals H times C over lambda, or wavelength. How do I need to know that I must use this formula? We want E, we know H, we know C, those are constants. They will always be a particular value, and we know wavelength. Done. Easy. So we can use that formula. So how it would look is as follows. We put the values in. H is 6.63 times 10 to the -34, like that. C is 3 times 10 to the power of 8. Notice how these are multiplied together, so I'm multiplying these two together. And wavelength is 700 times 10 to the -9 meters. Remember, we had to convert it to meters. Put brackets around everything. So you'll get a mark for your formula, substitution, 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 and then your answer. You type it into your calculator, you get your answer. So you need to use brackets around everything. and you type it just like that into your calculator, and this is what you get. My calculator actually says the following. It gives me this really long number times 10 to the negative 19. Some of my students ask me, ma'am, must you include that part? You absolutely need to include that part in your answer, and you can round off to at least 2 decimal places. So if you wanted to write this whole thing, you absolutely could have, but I just rounded it off to 2 decimal places, which is why I said 2,84 times 10 to the negative 19, and we worked out energy, which means my unit is joules, J. Without the unit, you cannot get an answer mark. So that's one way to get to the answer. What you can also do is the following. You can use 2 separate formulae. So in this particular test, that is how they gave it on the formula sheet. 2 separate formulae like that. Remember, I showed you that you can combine it into one formula, but you don't have to. You can use it as 2 separate formulas. Just please take notes, and I do go over this in my electromagnetic radiation calculations video, which again, I'll link below. But C is the speed of light, which is a constant. It's 3 times 10 to the power of 8, and it will always be that for all types of electromagnetic radiation. So you see here, they say that a photon of electromagnetic wave. That means it has that speed immediately. So instead of using V equals F lambda, or F times wavelength, they're using C. Because it's a constant, it'll always be that value. And H is also a constant. It's 6,63 times 10 to the negative 34, and it'll always be that value. In this way, if we do both formulas, you need to write the formulas of both of them down. Then I know that that's a constant, 3 times 10 to the 8. I don't know the frequency, but I know the wavelength. Remember, we had to convert it earlier to meters by timesing by 10 to the power of 9. Then I solve for frequency first. So this is times 700 times 10 to the negative 9, so I must divide by 700 times 10 to the negative 9. Remember, I'm taking this left-hand side of the equation and dividing it by that. Use brackets, please, grade 10s, or whoever is watching this video, grade 11s, grade 12s, you need to use brackets or your calculator is going to be confused. What I get now listen to me very carefully, is a number that goes like this. 4,285 714,286 times 10 to the power of 14 hertz. Am I at the end of my question? And I always ask my students this question. Did they ask me to calculate the frequency of the wave? No, they asked for energy. So this is not my final answer. And because that's not my final answer, I cannot round it off. Please, cannot round off. You never round off in the middle of a question. I'm going to use that in my next formula, and I need to use it non-rounded off. So H is 6,63 times 10 to the negative 34. It will always be that. It's on your formula sheet, and I multiply it by that long number that I just got. Remember, don't round it off. You're going to multiply it by that entire number. So I just kept it on my calculator, and I'm multiplying it by the constant. And doing that, you get exactly the same answer as what I got when I used the combined formula. 10 to the power of negative 19 joules. Take note, exactly the same answer. Okay, so in this case, I'm just using 2 separate formulas. You'll get formula, substitution, final answer. 5 marks. 5.5 says, how will the energy of this photon be affected if its wavelength decreased? Okay, so E is equal to H times F, basically. We know frequency is equal to, or let's write it like this. So if wavelength is decreased, let's start here. If I make wavelength smaller, speed of light will always be the speed of light. That's always going to stay the same. So if I make wavelength smaller, what's going to happen to frequency? It's going to get bigger. And you should remember that from a few minutes ago. I said if you have a small wavelength, so if I decrease the wavelength, if I have a small wavelength, you will have a big frequency. They do the opposites of one another. They are inversely proportional. That's a nice word to use. They are inversely proportional. They do the opposites of each other. So that means if wavelength is small, frequency is big. And if frequency is big, so if this is big, energy is big. And the reason why is because energy and frequency are directly proportional. And I did mention that earlier on as well. I said if you have a high frequency, like gamma rays, you have a high energy, which means you're quite dangerous. So if I decrease the wavelength, frequency gets bigger, which means energy gets bigger. Okay. Another formula that you can use, so the answers increases. I'll give a proper reason now, but another formula that you can use in order to, figure this out is this formula over here. If wavelength gets smaller, so this is a fraction. If wavelength gets smaller and smaller and smaller, think about how fractions work. What happens to energy? It will get bigger and bigger and bigger. Okay, that's because energy and wavelength do the opposite. They're inversely proportional. So that is exactly what the past paper memo says. If you want to look at a formula to help you, you look at this one. If wavelength goes down, energy goes up. They are inversely proportional, which means they do opposite things. And that's basically a reason. Okay. Or you can explain the long ways. You can say, if wavelength goes down, frequency goes up. They are inversely proportional, right? That's our first step. Inversely proportional. And if frequency goes up, energy goes up because of this formula. They are directly proportional. So it's kind of like our calculation question. You can either explain it using one formula. If that goes down, that goes up. Or you can do it using two formulas. If this goes down, this one goes up. And if frequency goes up, energy goes up. I hope that makes sense. This is supposed to be a more difficult question to answer. Right. Moving on, we've got electrostatics. So don't run away yet. We've got quite a lot of well, not a lot, but a decent amount, to prepare you. And then we've got some circuits. So the electrostatics question, it says two identical insulated spheres, X and Y, are suspended from threads. They're held at a small distance apart. Sphere X carries a charge of 6.4 times 10 to the negative 18 coulombs. They give it to you in coulombs, and just a warning, grade 10s, if they don't give it to you in coulombs, so if they give it to you in nano coulombs or milli coulombs or micro coulombs or pico coulombs, you have to convert, just like we did earlier with meters. But in this case, we're lucky because they give it to us in coulombs. Sphere Y has an excess of 30 electrons. Now, they asked me a bunch of questions, but the first thing that I want you to notice is that they actually label sphere Y as negative. But even if they didn't label it as a negative, how would I know that it's negative? Well, it has an excess of electrons. We know that electrons are negative. So if you have an excess of electrons, in other words, you have a lot of electrons, you have more electrons. Electrons are negative, which means if you have a lot of electrons, you are negative. It has an excess of 30 electrons. So not one electron, not two, not three, but 30. 6.1 says calculate the magnitude of charge on sphere Y. Now, early on in the video, we discussed how one electron has a charge of negative 1.6 times 10 to the negative 19 coulombs. If you have two electrons, then you take the charge of an electron and you times it by 2. If you have 3 electrons, you take the charge of an electron and you times it by 3. This sphere has 30 excess electrons. So you take the charge of an electron and you times it by 30. And that's basically how we get our answer. The proper formula that we use, and we can see it on the formula sheet, the proper formula that we use looks like this. Some formula sheets give it to you looking like this or like this. I'm just showing you all the different versions. They all mean exactly the same thing. N is number of electrons, Q is the change in charge, and QE or E or QE, however they say it, is the charge of an electron. So what we do is we write the formula first. N is equal to Q over QE. N is number of electrons. So this sphere has an excess of 30 electrons. So in the place of N, number of electrons, we put 30. Q is what we're looking for. We're looking for the charge on Y. And QE is the charge of one electron. Negative 1.6 times 10 to the negative 19. And you could say, ma'am, where did you get that from? It's given to you on your formula sheet. There it is. Negative 1.6 times 10 to the negative 19. So that'll always be given to you. It's a constant. Use brackets, please. When you type this into your calculator, you say 30 times negative 1.6 times 10 to the negative 19. And we get negative 4.8 times 10 to the negative 18 coulombs. Your unit is coulombs because you're calculating charge. The formula, substitution, answer with units. Okay? The spheres are allowed to touch each other. After touching, they move away from each other. Okay, cool. So we've got a positively charged sphere, negatively charged sphere. They touch. When they touch, you guys need to know that electrons are transferred. And electrons are always transferred from the more negative sphere to the less negative sphere. Or the more negative sphere to the more positive sphere, basically. That's how electrons are moved. First, they want us to state the principle of conservation of charge. This is just something that you need to study. You need to learn it. It's a definition, and you need to know it off by heart. And that is the definition. The total charge in an isolated system, you have to say the total charge, or you have to say the net charge. Total or net, you have to say one of those words. The total charge in an isolated system, you must say that, remains constant. And some definitions include during any physical process. So I would recommend that you add that to your definition. During any physical process. You need to say the entire definition in order to get your 2 marks. You can't leave out important words like net or total and isolated and constant. You have to say those things. 6.2.2 says give a reason why the spheres move away from each other after touching. So what you should know is that before they touch, this one is a positive and this one is a negative. So they have opposite charges. And you should know that opposite charges or unlike charges attract each other. However, when they touch and electrons are transferred, remember electrons will be transferred from Y to X because it's from the more negative to the less negative. And when they transfer electrons and then they separate again, they will end up having the same charge. And when they have the same charge, that means that they will then repel each other because like charges or the same charges repel. So there's your answer. Both spheres will carry identical charges or the same charges, and like charges repel. That's why they move away from each other, because they repel. Okay, calculate the charge on each sphere after they've separated. So you need to know that when objects come into contact, they touch each other and they separate. To calculate the charge after they separate, we need to use this formula. Looks like this. Q equals Q1 plus Q2 divided by 2. Because it's 2 objects, we divide by 2. If there were 3 objects, we would divide by 3, and so on. What we then do is we substitute in the charges. So Q1, there's the charge, 6.4 times 10 to the negative 18 plus Q2, we just calculated that in a previous question. We got it over there. Negative 4.8 times 10 to the negative 18. Negative 4.8 times 10 to the negative 18. You do have to put the plus and the plus or minus signs in here. Note how the formula says plus, that's where the plus comes from. And the minus is because sphere Y has a negative charge. You must substitute that in there. We divide it by 2. Once again, I do recommend using brackets on your calculator when performing these calculations. If you don't use brackets, your calculator can sometimes get confused with what you're saying, especially when you're dealing with scientific notation. And our answer is 8 times 10 to the negative 19 coulombs. What that means is now, after they touch and separate, both X and Y have the exact same charge. 8 times 10 to the negative 19 coulombs, positive charge. Y also has 8 times 10 to the negative 19 coulombs, also a positive charge, and that's why they move away from each other. They repel each other. 6.3 says a neutral sphere Z is placed next to sphere Y as shown below. So as we mentioned already, at this stage, X is positive and Y is also a positive, and they are repelling each other like this, and then they replace a neutral sphere Z over here. Now, they say, what is meant by neutral? Now, what you need to understand by neutral is that it has a charge of 0, but more importantly, what that means, 0 coulombs. More importantly, what that means is the number of protons and the number of electrons is equal. So say, for example, it has 3 protons and 3 electrons. Overall, it has a 0 charge. That's what neutral means. So it doesn't mean that it has no charges. It just means that the positive particles, the number of positive particles or number of protons, is equal to the number of negative particles or electrons. And that is my answer over there. If you want to, in your answer, you can add in that neutral also means that it has a charge of 0 coulombs. But most importantly, number of electrons equal to the number of protons. 6.3.2, use a sketch to show how the charges rearrange themselves inside sphere Z. So remember what I told you about neutral. Z is neutral, has a charge of 0. It doesn't mean that it has no electrons or no protons, but it means that the number of protons and electrons are equal. However, when Y and Z are close to each other, remember Y is positive, and positive charge attracts negative electrons. Remember, only electrons can move. So what it means is the electrons on Z, sphere Z, will get attracted to Y. Why does it get attracted? Because remember, Y is positive. So the positive sphere Y attracts all the negative electrons on Z. So it leaves this side of the sphere more negative and this side of the sphere more positive. And basically, grade 10s, this is called polarization. So if they say, what is the phenomenon called? When this happens, it's called polarization because this is the negative pole and this is the positive pole. But they didn't ask me what the phenomenon is called. They asked me to draw a sketch to show how the charges rearrange themselves inside Z. So what you'll do is, this is Z, just label it as Z. You'll show me that the electrons move towards the one side of Z. So they move to the side of Z closest to Y because Y is positive, and this side will be more positive. Okay. So what that means, I just want to make it clear, is it doesn't mean that this left-hand side here has no positives. There will be some positives, but it has more electrons. So this is exactly what the memo looks like, and they give 2 marks for that. Right, our last question that we'll do is our electricity question. So let's jump right into that. The circuit diagram below indicates that there's 2 resistors connected in parallel, R1 and R2. Note how there are no other resistors connected in the circuit. They tell us to ignore the resistance of the battery and the wires. Switch S is initially closed. First question, define the term potential difference. You can see that these are all the questions we'll be answering. 7.1 is just a definition. It's something that you must study. It's the reading across the terminals of a battery when current flows in the circuit. What you do need to know in grade 10 is that when the switch is closed, the reading on the voltmeter connected across the battery reads the terminal potential difference. Terminal potential difference. If I open that switch up, so it's not closed anymore, it's now open, that voltmeter connected across the battery will read the EMF. That's all you need to know about EMF in grade 10. Okay, cool. Calculate the reading on the voltmeter V if the battery transfers 3 times 10 to the power 4 joules of energy per every 2.5 times 10 to the power 3 coulomb of charge that flows through it. Now, you should recall from our electricity lesson that another definition for potential difference is the amount of energy per unit charge, or the amount of work done per unit charge. That is the formula for voltage. And I hope that you can recall that lesson. And if you haven't watched it, I do suggest you go watch it. But that I just showed you is basically this formula over here. So voltage or potential difference of a battery, V, is equal to the work done or the energy transferred per means divide, unit charge. Unit charge is Q. Charge is Q. So what they're doing in the question is they're asking us to calculate the reading on the voltmeter V, which means they're asking us to calculate voltage or potential difference. They're giving me energy or work, 3 times 10 to the 4 joules of energy. And remember, I told you guys that work and energy is the same thing. So work or energy is 3 times 10 to the power 4 joules. Per every 2.5 times 10 to the power 3 coulombs of charge. Charge is 2.5 times 10 to the power 3. So what we do is we write the formula that we're going to use, which is this formula over here. You substitute in what is given. So they give me the work or the energy. It's 3 times 10 to the power 4. they give me the charge. It's 2.5 times 10 to the power of 3. Use brackets, divide them, and you should get your answer for voltage or potential difference, which is the reading on the voltmeter, which is 12 volts. Remember, you're reading the reading on the voltmeter, it's measured in volts. That's it. This is one formula that we can use in order to work out the reading on a voltmeter or voltage. 7.3 says, determine the reading on ammeter A3, so here's A3. If the reading on A1, that's A1, is 1,62 amperes, and the reading on ammeter A2 is 0,65 amperes. So now just a little bit of a recap about circuits. Through the battery, and through this part of the wire, and through A1, that is where total current flows through. Total current flows through this part of the circuit. As soon as you see a split in the circuit, so here is a split in the circuit, then that total current, that 1,62 amperes, splits. Some of it goes through this branch, and the rest goes through the bottom branch. So with that knowledge that current splits in parallel, we know that 1,62 amperes will split. So some of it will go through the blue branch, some of it will go through the green branch. So basically A1, the reading on A1 is equal to the reading on A2 plus the reading on A3. So the total current, the yellow, is equal to the blue current plus the orange current. So basically all we do is we take our total current, 1,62, and we minus 0,65. That leftover current is the red current, the current going through A3, which is 0,97 amperes. Remember, you don't write amps. I said this in my electricity video. You don't write amps as a unit. You can write out the full word amperes, or you just use the symbol A. So basically what this is telling me is 1,62 is the total. The reading on A2 is 0,65. To get A3, we take that over and it becomes 1,62 minus 0,65. I hope that makes sense. 7.4 says, how will the resistance of R1 compare to that of R2? Now, remember, we know the total current was 1,62 amperes. We know this reading on A2 was 0,65 amperes. And we know the reading on A3 was 0,97 amperes. Now, what you also should know from my electricity revision video that I have on my channel is the following, and that is the smaller the current, the bigger the resistor. So this is current 0,65, this is current 0,97. Which one is smaller? This one is smaller. So the smaller the current, the bigger the resistance. So how will the resistance of R1 compare to that of R2? It will be greater than. R1 will have a greater resistance. So, and the reason is because it has a smaller current. And I think that will be the next question. No, they actually don't ask me for a reason. But basically, the reason, if you had to give a reason, was because that the smaller current travels through R1, which means it will therefore have the biggest resistance, because current and resistance are inversely proportional. Inversely proportional means they do the opposite thing. Okay, so if they had to ask for a reason, that would be a reason, because voltage is constant. And the formula that we use for that relationship is this one, or V is equal to I times R. So if voltage is constant, if this number is very big, this number is very small. This question, switch S is now opened. Remember it was closed? Now we're going to open it. What term is used to describe the reading on the voltmeter? Now remember, when the switch was closed, the reading on the voltmeter, this reading over here, was called the terminal potential difference. As soon as you open the switch, the reading on the voltmeter across the battery becomes the EMF. And that's it for this paper. That is 75 marks. We just completed the whole paper. Thank you for staying with me to the end if you did. If you're one of the people that stayed to the end, comment down below so I know who the truly dedicated students are. I hope you subscribe for more videos like this, and I can't wait to see you guys in future videos. Bye, everybody.